All right, David, you said you had some answers. Do you want to maybe share your answer for the first question?
Yeah, so in your slides, it's stated for waves to be guided with TR and no losses, and G should be smaller than NC.
Yep.
And if we look at the at the graph, we can see that from around 800 and onwards, the
exactly
core is what do you say?
The core index is higher than the
ratio of reflective indexes.
All right, excellent. So can you maybe just think out loud? What do you think, or what would be the difference in the input angles when you're using this waveguide around, let's say, 900, or when you're using it at 1600? All right, maybe someone else? Anybody else want to try a guess? No one wants to try a guess.
Maybe I have to look at the equation, but my intuition would say the input angle for higher wave numbers, it can be relatively sharper than lower wave numbers.
Okay, so first of all, be careful when you use the word wave number, because wave number is k, and that's 2 pi over lambda, and that's actually, it's for higher wavelengths.
Yeah.
So why? But in this particular case, why do you think it's for higher wavelengths? Because it's, Why at higher wavelengths? Would it be more angles or steeper angles?
Yeah, I don't have a reason yet.
All right. Anybody else want to give it a shot? All right. At random. Yeah, Eve?
Yeah, well, it says that theta C depends on NG divided by NC.
Yeah.
But I don't know what the A cosine does, if it grows bigger or smaller, if the NG divided by NC goes bigger or smaller. But I would have to calculate that to see, but.
Well, roughly speaking, what you can imagine is that the angle can be bigger because the ratio is going to be also larger. So the angle, the theta C, is going to be theta C on, so theta C is going to be larger. So the permitted angles will be larger as well. Okay? And so basically the reasoning here was that the around 1,000, the difference is much smaller. So you're much closer, because the criterion is that if your two indexes are exactly the same, then the theta C is the inverse cosine of 1, which is an angle of 0, right? And so an angle of 0 means that the only rays that are going to be guided are the ones that are at an angle at 0. Any other ray is going to be refracted and lost. So that's why when you have a larger difference, then this value increases. Okay, so you're absolutely right in saying that it's the ratio that's important, not just the difference. But if you can kind of guess.
Remind me 1 hour that wasn't.
Say that one more time, Cyril.
Yeah, that was my roommate, but I wanted to ask if you have an your first corner, your intended wave, if that has an 0 degrees, it's already never coming out, right?
Yeah,
It's an,
exactly. So
yeah, sorry.
if it's exactly 0 degrees, it's never going to bounce on anything, but this is an idealized scenario. So you have to imagine, even if your angle is very, very small, because this waveguide is theoretically infinite on the right here in the Z direction, it will eventually hit the side, and then it will refract and it will come out. Okay?
And if you bend the fiber,
Exactly.
then it will come out.
Exactly.
Okay.
Yeah, that's exactly right. So then bending of fibers is something a little bit later, but yes, when you bend fibers, not super sharp bends, but when you bend them slowly, you do change the angle a little bit, and then you may have some losses. Okay, so the second question. Who wants to say what they think happens to the 10 picosecond pulse? Maybe Emma? Unless someone else is dying to. Emma, maybe? Going once.
I believe your mic was broken the last time, so maybe
okay.
still.
All right, that's fine. M. Sleba? I don't know your. I don't know if Sleba is your first. I don't think your Sleba is your first name.
That's my last name.
Okay, what's your first name?
Martin.
Martin. All right. All right, go ahead, Martin. What do you think?
Well, the wave is going to be longer because the light travels slower in the medium than just normally.
Okay. So the question says you have a 10 picosecond pulse at 1500. What's the longest possible what's the longest possible path, and what's the shortest possible path along your waveguide? So if we look at this waveguide, which path is the longest and which path is the shortest?
That depends on the incident angle, right?
Well, let's say the incidence angle is something you can change. Which one is the longest and which one is the shortest?
Steeper incident angle will be longer because then it will bounce more often.
Exactly. So what's the maximum angle that you can have on what's the maximum theta z?
90. Probably won't go.
No, because what happens if your theta z is 90? Then your ray is going straight up.
Yeah.
And it's going to just leave the waveguide. So what is the maximum theta z that you can have?
Yeah, that depends on the theta c that you calculated earlier, right?
Exactly. So the longest, and which one would be the shortest?
0.
Exactly. Going straight through the middle. Okay. So that's exactly right. So now the question is, does anybody have a value for what the difference is between the shortest and the longest, either in terms of time or in terms of distance? Manuk, maybe? No Manuk?
No, I have no value for that.
Okay. Shalice, maybe? Okay. And Shivara? Sorry if I'm mispronouncing some names. Okay, well, does anybody have a value?
I have one, but I noticed that I used sine instead of cosine, so it's wrong.
Okay. Well, try. Just explain how you did it.
Let's see, what did I do? Oh yeah, of course I calculated the critical angle, but I used the sine for instead of the cosine. And then I calculated the optical path length via the geometrical path length.
Okay.
And that would be 100 meter and 27 centimeters according to my calculations. But
100 meters and 27.
and then the other option would be just the length of the fiber times the breaking index.
Yep. So what you have here is it's exactly what you described, Eve. So if you look at 1500, you can find the values for the index of refraction, and then based off of the equations, you can find the geometric path and the corresponding optical path. Okay, so what happens here is if you do the if you crunch the numbers, you see that for 100 meters, for 100 meters, you actually see it takes about 500 nanoseconds for the pulse to get there, and or 492, and then the difference between the shortest length and the longest one is about 1 nanosecond. So that means if you send your beam of light, onto your waveguide, part of that, let's say part of that light takes the shortest path down the middle, but part of that light also takes the longest one, and then also all the other combinations in between. What's going to happen is that your pulse is going to be spread out over the time that because of the travel time through the glass, part of the pulse is going to arrive at a certain point in time, the earliest one, and then the pulse is going to keep arriving until the last chunk gets there. And so what effectively happens is you have pulse spreading. So originally your pulse was, let's say, 10 picoseconds, and now it's spread over 1 nanoseconds, which is 100 times longer than what it was in the beginning, and that's only over 100 meters. So now imagine what happens if you're using this for telecom applications, and this is your internet that you're sending, and you have cables that run kilometers and kilometers. Your pulses are going to be super spread. Okay, so can anybody try and guess maybe why that might be an issue? The fact that the pulses are spreading.
Yeah, your signal will be noisy.
Yeah. Okay, keep going. What do you mean by noisy?
There will be a delay in certain signals, so they won't come in at the same time, or in the order you want it to be.
Exactly.
So especially with telecommunication, you could hear if I over exaggerate, you would hear certain sounds earlier than others.
Exactly. So it's exactly that. Part of the information, the information wouldn't all come at the same time. So let's say we're sending a binary signal. So it's just ones and zeros. So it's active laser is 1, and the laser's turned off is 0. If you now send one pulse and then you send another pulse, and they're too close together, they're going to spread out so much that they're going to overlap, and you won't be able to differentiate them at the output. That's in telecommunications. That's why that kind of stuff is a huge issue. So here we're seeing one of the limitations of waveguides.
Right.
Okay. And so the second part of the questions, in the BMO course, can you think of any application where that might be a problem?
Optical OCT, right?
Yeah. Why?
Because if you with OCT you want to know the exact spot of certain parts of the eye, for example, and if you have a time delay in it with certain signals come earlier than others, you get you could see spots, which would mean certain illnesses or diseases, but which actually are an error of the system.
Exactly. That's exactly right. So in optical coherence tomography, what you're measuring is the delay time between your reference mirror and whatever it is that you're looking at, right? But let's say you have, I don't know, here the example is 100 meters of this waveguide. In an OCT system, you typically have, I don't know, between 5 and 15 meters of fiber, right? Well, that's fiber, but like if you have this, so part of the answer here is also figuring out the difference in distance, right? So the path length difference over this 100 meters is on the order of what was it? It's about 30 centimeters. Yeah. So the shortest path length versus the longest path length is 147 meters. So the optical path length is 147.6 versus 147.9, right? So that means that you'd have a 30 centimeter difference between the shortest and the longest, right? So in OCT, even if you have much less fiber, let's say you don't have 30 centimeters of difference, but you have one order of magnitude less, so let's say 3 centimeters. In OCT, the things that you're trying to measure are all located within 5 or 10 microns of each other. So you'd have signal that's coming from from a reflector that would come from, let's say, position 0, and it would also look like it's coming from position that's 3 centimeters behind that, which is already way outside of your imaging field. Okay, so that's exactly why it's a problem in OCT. So another thing that can happen is this difference in path length can also affect the pulse itself, the pulse shape, right? And so what happens is the energy of the pulse is going to be spread out over a longer period of time. Now you saw in your, I think, stop me if I'm wrong, but in your classes you saw a little bit about photodynamic therapy and photoablation and the different regimes. And if it's very, very long pulses, then you tend to heat the tissue. And if it's very, very short pulses, then you tend to do ablation or more drastic therapies, right? So if you use this waveguide to get inside the body, and then it turns your very, very short pulse with very, very high peak power into this very long pulse, instead of ablating the tissue, you're going to end up burning it. And that's a huge problem if you're for your therapy. Okay? So that was just a mini assignment just to highlight some of the issues of just basic waveguides and how, and this, like, what we're going to be discussing is why fibers are a little bit more advanced than that, and how they still work even through these issues. Does anybody have any questions? Is everything okay?